We are going to talk about the following topics for today. Some simple multiplication facts, next we want to talk about expressing systems of equation through the multiplication of matrices. So a linear system of equations as matrix multiplication, as an example of a matrix multiplication. Then we want to talk about expressing substitution as matrix multiplication. Finally, if you have time, we are going to talk about different ways of looking at matrix multiplication. We have looked at one of them, like the one we just talked about. There are other ways of describing comes in handy when you can look at this rather complicated process from different kind of perspectives and use it in different style. Okay, let's practice matrix multiplication in some special cases. That is, we are going to take a look at the special matrices and multiply some arbitrary matrix by a special one to see what happens. If you take two totally arbitrary matrices and you want to multiply them, it's such a big mess of arithmetic that's kind of hard to see what's going on. So we are going to take a look at some special matrices. Now there is a very long list of matrices that you could consider special. The ones that we are going to pay attention to is the ones that have special zero structure. That means they have a lot of zeros in them. Zeros make life a lot easier for us when you're doing multiplication. So special matrices that we have are showing just lots of zeros in them. Of course, you could go to an extreme and just pick a zero matrix. Of course, that life becomes just too easy then. If you take a zero matrix and multiply by any matrix, if you could multiply them, what do you get? Just as in basic algebra, you still get 0. So from now on, we are not going to talk about compatibility. Whenever we write multiplication, we assume that you can actually multiply them. So 0 times anything is just zeros. That is not all that interesting. Next, special matrix that is not so trivial is a matrix that's going to play the role of 1 for us. You know, in basic algebra, 1 times any number is just that number. Take any number, you multiply by 1, you get just that number back. We might ask ourselves, what's a matrix that plays that role, that is, plays the role of 1 among matrices? That matrix is called the identity matrix. So what is the identity matrix? Anybody has any guess? Has ones on the so-called diagonal, and everywhere else is 0. So to indicate that, we write it like this. We have ones on so-called main diagonal. So each rectangle has 2 diagonals, or each square has two diagonals. We are just calling this the main diagonal, and the second one we are really going to deal with that. So one's on main diagonal and zeros everywhere else. Well, how big is going to be? Well, depends how many rows and columns you got. If I write I sub n, that means I have n rows and n columns. For example, I3 would be 1 0 0 0 1 0 0 0 1. So I3 is a 3 by 3 square matrix. On the diagonal we have just ones. Everywhere else we have zeros. We have 6 zeros. So what is so big deal about this? If I take I3, let's just take that one and multiply it by some matrix. Let me just choose that one also to be a 3 by 3 matrix for now. So what happens? We learned how to multiply matrices last time. So I take this row, multiply by this column. Who is going to be picked out? 1 times A, so it's going to be A here. When I multiply by this, it's just going to pick out what? B. Multiply by this, it's just going to pick out C. So here I'm going to see A, B, C. If I go to the next row, if I take this next row, multiply by that, it's going to pick the second element of that column. Is that right? Because 1 shows up as the second entry. 0 times A is just 0. 1 times D, I'm going to pick out the D, and 0 times G, that's going to vanish. So I'm just going to pick the second element here, and second element here, and the second element here. So we are going to have D, E, F showing up in that spot. And then if we go ahead and pick the last, oh well, that was a good idea. If we pick the last row here, we multiply, we just recover the last entries here. So G, H, I are going to show up. So the advantage of this particular matrix is that when I multiply by anything, it just preserves it exactly as it is. So what we have, again, not getting tangled with the issue of the size and compatibility conditions. If you multiply I with A, you get identity. And if you try the other way, again you get, you get the matrix back, and here also you get the matrix back. So that is one special matrix we have. Now, there are many other matrices not talked about in the text, but maybe it's as good of a place as any to talk about them. Next matrix that kind of looks like this, but not quite, it's called the diagonal matrix. Diagonal matrix has the same zero structure as the identity, except that now on the diagonal we could have any number, not necessarily just a bunch of ones. So an example of a diagonal matrix could be like the following. Say 2, 3, 5. I multiplied with A, B, C, D, E, F, G, H, I. Now what I'm expecting from you to give me a verbal description of what is the net effect of this multiplication. You might want to do a few of them to see how to describe what it does. What does it do? So when I take 2 multiplied by these guys, what does it do? It doubles them. Is that right? And then you said what is a scalar for each of these. So I take the second row, multiply by each of these. The net effect of that is to do what? Triple the second row. And what do you think last one is going to do? Of course, quintuple the last row here, so it's going to 5G, 5H, 5I. Now, let's see, it's going to become interesting. Now, A, B, C, D, E, F, G, H, I. What if my diagonal matrix showed up on the right? getting used to the fact that things on the left and right are going to do different things, and we have things called rows and we have things called columns. It's a fact of life in linear algebra. You have to, if you get confused about it, always pick out some small size matrices, 2 by 2, 3 by 3, just do it there, and that refreshes your mind as to what's going on instead of trying to memorize. Anyway, we are going to do the same business as before. So if I take this and multiply by that, you remember row of this and column of the second one, and that is supposed to, so ABC times 200 is going to give me what entry here? So of course 2A. Now just to see what the effect is, I go down through this list. I go through the rows while all the time looking at the same column. Of course you could have done anything, but just to see. DEF times 200 is going to give me what? 2D here. Is that right? This is the second row, first column, 2D here. Third row, first column, what am I going to get here? 2G. And then who is going to be, maybe you get the hang of it, what's going to happen on the second column here? They're all going to triple. Is that right? Because you multiply ABC. So I multiply this by that. It picks out only on the second entry. The second entry of that, second entry of this. So second entry of each column is going to be second column. So what we have is 3B, 3E, and 3H. And what do you think is the last round going to do? Multiply this thing by 5. So 5C, 5F, 5I. So diagonal times the matrix, the effect is that rows are scaled. What do you mean? Each row was scaled by entry on the diagonal. If you have an arbitrary matrix multiplied by a diagonal, this one, the columns are scaled. Okay, so the special zero arrangements that you make in a matrix through multiplication, they show themselves doing special things. We are going to see a lot more of these things when we come to detailed explanation of Gaussian elimination. Gaussian elimination, they are a special type of matrices really, and they do special things for us. We are going to single them out and talk a lot more about it. But let's postpone that for a while so that we finish the official component of 1.3. So next issue that we have, we said we are going to talk about, what are we going to talk about? So we talked about this one, certain special cases of multiplication. We paid attention to them. Next issue is that if you have a linear system, that linear system is in fact a form of matrix multiplication. Let's just write a simple one. Suppose we have 2x plus 3y is equal to 5, and 7x plus 9y is equal to 11. Okay, this is a traditional format that you have seen since junior high. Okay, that's how you write it. Now we want to take this, so this is traditional style, and we want to write it in the matrix style. Matrix style, we say we have a matrix of coefficients. These are the numbers, 2, 3, 7, 9. Of course, you have to have your variables lined up in proper columns. That matrix, so this is a coefficient matrix, we called it. Then we have a column of unknown quantities, or the variables. And then we have the numbers on the right hand side, 5, 11. I typically refer to this thing as simply as the right hand side vector or something. Sometimes the text refers to it as a constant matrix, but this is also a constant matrix. So let's double check to make sure we understand why these two things are actually same. If I take that, multiply by this, what do I get? I get 2x plus 3y, which is this. And when you say that is equal to that, it means that you are stating that the result of this multiplication is that entry over there. And similarly, if you are multiplying 7, 9 with this xy, you are getting 7x plus 9y. And when you say it is equal to that, it means the result of this multiplication is equal to the corresponding entry on the right hand side. So a matrix style just represents matrix multiplication, can show a traditional system of equations. So what you have here is a linear system. Linear systems could be shown like this. So linear system is made out of a coefficient matrix. This is typically shown by some matrix name. They call it A, B, C, whatever. Then you have a column of unknown quantities. Traditionally, again, you call it X, Y, Z. So here X, capital X, refers, or bold X, refers to a list of your unknown quantities. On the right hand side, you just have a column of typically fixed numbers and such, and this one you might want to refer to it as just B. So that whole thing makes the equation look deceptively simple, that this equation, that your system of equation you're looking at, has this simple representation. A matrix times another matrix is equal to a third matrix. This is a coefficient matrix. Typically lots of numbers here is an array. This is a vector of unknown quantities. Right hand side, typically a vector of known quantities. So from here on, when I say consider the linear system AX equal to B, you have to kind of train your mind into just seeing through this deceptively simple statement. The left hand side is really a huge number of things shown by a very simplistic looking convention. It just looks like those things that you have seen in 6th or 7th grade. Over there you might have seen 2x equal to 6. This is just looking like that. How would you have solved this? Well, you divide by 2. Here we want to figure out how to divide by A. We have to spend quite a bit of energy to, over there it was kind of easy to say, okay, multiply by inverse of 2 or divide by 2, however you want to say it, and you get x is equal to 3. Well, the equivalent of the same thing here is going to take us about half of the semester to do. It's not as straightforward as it looks over there. Now, okay, so we handled this issue as well. We talked about expressing a linear system as a form of matrix multiplication. Next fact that gets to be represented by matrix multiplication is substitution. That ordinary substitution you do in many problems, that is also in fact a form of substitution. So all of these things is going to give credibility to our definition. We gave a very peculiar definition for multiplication, and one by one these things show their themselves as a matrix multiplication. So now we are going to take a look at that. So substitution as a type of multiplication. Now just to do kill two birds with one stone, maybe I'll just pick out one of the problems from this section. Make sure I'm picking something that's not a sign problem. Just do that, and those two items at the same time. So problems in this section that are related to this topic, from section 1.3, problems from 21 through 24 are of this type, and 21 is assigned, so maybe I just do say 22. Let's take a problem 22. Okay. The idea is that you start by some expression or maybe in an equation. So I have some typical equation like this. We are not trying to solve it, rather we are trying to manipulate it. So I have some expressions here in the form of a linear system. And then substitution kicks in by saying that perhaps x, y, z are themselves linear expressions of some other variables. For example, x is given to us as 3p minus q. Y is given to us as p plus 3r. Z is given to us as q minus r. So what is the idea? The idea is that we want to substitute these over there. This is just like the substitution equation. Again, you have seen in algebra 1 and 2, like you calculate x in terms of y and you substitute it in the second equation. Well, this is a more general form of substitution of that type. For whatever reason, perhaps we want to substitute x by some other stuff, y by some other stuff, and z by some other stuff. So we can go and just substitute. It looks like a mess of juggling things around. But when all dust settles, we are going to see that really what we have done is a kind of matrix multiplication. We could have made the whole thing look very neat and clean and not so messy looking. First, let's go ahead and do it messy style. Messy style, we just substitute as we would have done in junior high. Say, okay, 5. Instead of x, you want this. Well, just put that instead of that. That's as significant as the request is. Minus 2y is the y. What should I put? So instead of y, I'm going to put this guy instead of y. So I'm going to have p plus 3r. And then plus z, instead of z, I am, this is playing the role of z. I just got one of the z's, and that is a q minus r. Right hand side, I could have had stuff too. I could have substituted there, but typically it's just a right hand side constant, so there isn't anything to do over there. Now our plan is to do this substitution over here as well, and then clean up. Or we might as well go ahead and do the substitution. So I'll have 4, same substitution, 3p minus q minus y, that is p plus 3r, plus 2z, which is q minus r, and that's equal to minus 5. Well, let's just do it depends on you if you want to rewrite everything or you want to do it in your head. Let's rewrite first time around. This is 15p minus 5q minus 2p minus 6r plus q minus r equal to 1. Just make sure I stay on this page. Let me squeeze as much as I can here. So I got 15p minus 2p, so that is 13p. Then let's deal with the q's. Minus 5q plus q minus 4q. Let's deal with the r's. How many r's do I get? So I'm writing it in the same order they were ordered here. So minus 7r is equal to 1. Same story again. 12p minus 4q minus p minus 3r plus 2q minus 2r is equal to minus 5. So let's see. Here are my p's. So 11p. Here are my q's. So minus 2q. And here are my r's. Minus 5r is equal to minus 5. So what did we achieve? We had that equation in terms of x, y, z. Now we have this other equation in terms of p, q, r. Just exercise in algebra. The question is there a neater way of representing the same thing so that it doesn't look like you're doing just drudgery here? Yes, if you remember that matrix multiplication systems themselves, a linear system has a matrix multiplication format. That is, if I take this, okay, help me out here. I take this and write it in the form of matrix multiplication. What should I write? My matrix 5, negative 2, what else? 1, 4 minus 1, 2, the coefficient we pick. And what is the next thing I have here? So I have x, y, z, and then I have my right hand side 1 minus 5. So I have 2 by 3 matrix times the 3 by 1 matrix. The result of it is 2 by 1 matrix, whatever. Now this fellow also has a matrix representation. So let's see. Help me out to do this one as a matrix style. What can I say? Like x, y, z, you can write it on the left or right, is equal to some matrix. Now read out the elements of that to me. What is here? 0. And 1, 0, 3, 0, 1, minus 1. Is that right? I'm just picking these guys out. Remember, there was no R here, there was no P here, so this is zeros. And there was no Q here. What do I multiply this thing with to get those X, Y, Z's? Yeah, it's just a P, Q, R. Now you tell me, how does matrix multiplication show its head? Question is, how do I get this one? Through matrix multiplication. Well, this is your x, y, z, is that right? Instead of that, instead of substituting the way you did, substitute wholesale. Take this guy, take this guy, and instead replace it by that. So tell me what to write. First, 5 minus 2, 1, 4 minus 1, 2. Instead of x, y, z, what should I write? Write all of that. So I write 3 minus 1, 0, 1, 0, 3, 0, 1, minus 1 times P, Q, R. Is that right? This guy is all of that. So I just substituted. Now this is a kind of a different substitution than what you have seen in high school, but it's still substitution. You're taking this guy out and replacing it by all of this, which is the same thing. What is my right hand side? We substituted this guy with all of this. My right hand side here is, yeah, my original right hand side is still there. So what do you bet? If I multiply these two matrices, what am I going to get? It's already on this page. But you are going to get these guys. You better get these now, guys, because that's the same substitution. So if I multiply this with that, I better get that 13. So let's see, do we? 5 minus 2, 1, 3, 1, 0. 15 minus 2, 0, that is 13. And so on. 5 minus 2, 1 times minus 1, 0, 1, minus 5. And a 1, that is minus 4. Times that one, what do we get? 0 minus 6 minus 1, that's minus 7. Right hand side, here's our ones. 4 minus 1, 2 times 3, 1, 0. 12 minus 1, that's 11. Times that, 4 and 2. Excuse me, minus 4 and 2. So I have minus 4, minus 2. Sorry. How about the last one? I have minus 3 and minus 2. That's my minus 5. Right hand side as expected. So what is the lesson? The lesson is if you have a linear system and the variables here are themselves expressed as another linear system, if you want to do the substitution, all you need to do is to pick the coefficient matrix of that, multiply by the coefficient matrix of the replacement. So what happened? Take the coefficient matrix of this one. That's what happens here. Here. This is the coefficient matrix of that. This is the coefficient matrix of the substitution. So really, this is coefficient matrix of original times coefficient matrix of substitution is equal to coefficient matrix of a new linear system. When you multiply, the coefficient matrix comes out of multiplying these two matrices. You have to keep the order intact, otherwise things get messed up. If you put that one first, this one second, things are not going to work out. So so that was a form of one more justification to give a significance to the multiplication that we have. It naturally expresses substitution. Okay, different ways of describing multiplication. Let's go back to see how have we talked about matrix multiplication anyway. We said you want to multiply two matrices. You want to multiply this one with that one and get another matrix. The way to do it was to pick a certain row and pick a certain column to get your result. So if I had row I and column J of this one, what I get out of this multiplication is element that is seated at the row I, column J. So this is still row I, and this one is still column J. So you do a dot product of these two, you get that entry, you're all set. Is there another way of describing the final result? Well, there are actually two other ways of doing it, and I guess for now I'll just get you ready for this discussion. We still need to talk about this thing on Monday, so we are still on month 3. This is going based on a row and a column. You might be wondering, well, what if I want to do a column and a row? That's possible too. It's kind of different outlook on life. So let's practice first multiplying a column with a row. Suppose I take 1, 2, 3, and I want to multiply this thing with say 10 and 100 and 1,000. It's a peculiar kind of multiplication. You don't see it all that often. They don't emphasize it. You haven't come across it. It didn't show up in your physics class or anything. So let me see if you can not fall in the trap and tell me what the answer is going to be. Here's my advice. Still follow the procedure that we have established and tell me what we get. Okay, what do we have? 10? Mm-hmm. Second row. So maybe I have to correct myself. You have actually seen something like this. Where do you see it? Back in 4th grade, maybe 3rd grade. When you make your multiplication table, what did you do? You had stuff here, and you just multiply them and make a big multiplication actual table. So this is different from what you were doing before, because over there you were getting just one number. row times a column was a scalar, was just one number. Here, a column times a row is a full matrix. So this is just like a multiplication table back in elementary school multiplication table. That's the flavor of it. What we want to do, or what we want to say next time, is that matrix multiplication could be thought about as a bunch of multiplication tables all compressed on top of each other. That is, if you take this guy and break it down now to a bunch of columns, break that guy to columns, and the second matrix, break that one to a bunch of rows. Multiplication of each of these columns with each of those rows is going to be one big multiplication table. If you take all those multiplication tables and just compress them to each other, which simply means add them all to each other, the sum total of all those tables is going to be the actual product of the two matrices we are after. So we are going to talk about that on Monday. So you want to continue with the problems of this section, and especially pay attention to so from 1-3 problems from 21 to 26. You want to do as many of these things as you can. Those of you who want to understand these topics at a higher level, try your best at 27 through 32. These are secondary importance unless you want to go to theoretical math. And then problems from 33 through 36. You want to do at least one of these guys as well. The remaining problems is going to require what I was just trying to do, which we didn't get to do right now. Okay, so we are going to leave that for Monday. Okay, so I'll see you on Monday.